You're watching Electrical Engineering Lectures channel. For more videos, please do like, subscribe and hit the bell icon for the latest notifications.
Assalamu alaikum everyone. In today's lecture of digital communication, we will be discussing the concept of bandpass modulation, and in particular we will be focusing on the coherent detection of one of the modulation schemes, which is amplitude shift keying. So let us first discuss the overall block diagram as a review of digital communication system. So this is the generalized block diagram of any digital communication system whose transmitter consists of the format block, which is responsible for the conversion of the information in the form of bits, followed by source coding, which is responsible for the compression of data in order to achieve high data rates. After that, we have channel encoding block, which is responsible for improving the performance of digital communication system by introducing redundancy in the data by introducing additional bits to improve the bit error rate performance. Followed by the next block, which is pulse modulation. This is responsible for the conversion of bits into the form of pulses or voltage levels, which are necessary to be made for the transmission. And the last block, which is mandatory block in wireless communication, is bandpass modulation, which is the topic of today's lecture. The purpose of this block is to convert the baseband pulse modulated data into the passband data through upconversion from baseband to passband. So both these blocks, which are pulse modulate and bandpass modulate, constitute the digital modulation structure. The bandpass modulated data will be passed through the channel, and after passing through the channel, the received data will go through the first crucial stage, which is demodulation and sample. So this block will convert the passband data to baseband and sample the data to serve to the detection block, and the detection block will use thresholding mechanism to generate the data in the form of bits. And the next block is channel decoding, which is completely inverse of the channel coding block. It will remove the additional data or additional bits that were introduced to improve the performance, followed by the source coding, source decoding, which will be exactly the inverse of source coding block, and followed by the last block, which is formatting, and it will generate the required information in the form of text or voice or video or any other format. So what is the concept of bandpass modulation? Bandpass modulation means the process of converting the baseband digital data into passband digital data, so that the data will be moved to a high frequency carrier. So the information that we want to transmit, we will transmit that information instead of directly transmitting it into the baseband signal. We will transmit the information in the form of a carrier whose one or more characteristics will be changing with respect to the information contained in the baseband signal. And those characteristics may include the amplitude of the carrier, phase of the carrier, or frequency of the carrier. So formally, the definition of bandpass modulation will be the process of converting a data signal to a sinusoidal waveform where its amplitude, phase, or frequency, or a combination of them, are varied in accordance with the transmitting data or baseband data. So we will be changing the amplitude, frequency, or phase, or a combination of these three characteristics to convert the baseband data into passband, and actually we will be mounting the information that was contained in the transmitting data into the carrier. So the generalized model of the bandpass signal will be in the form of a carrier whose amplitude, shown by this particular amplitude 2ei over capital T, here 2 and t are constants, and the amplitude variation is only governed by this factor ei, where I is from 1 to capital M, assuming M-ary bandpass modulation. And next is cos omega ct. His omega c is the carrier frequency, which is fixed, but there are two more arguments in this function, in this cosine. The first one is I minus 1 into delta omega into t, and the next one is phi I of t. So the first one is responsible for the change in frequency, and the second one is responsible for the change in phase. So gt of small t, that will be called the baseband pulse shape, which is used in the pulse modulation block Here, for simplicity, we will be assuming that this pulse shape is in the form of a rectangle, although rectangular pulse shapes are not physically realizable. But in order to have the main concept only, for simplification, we may assume that this is a rectangular pulse, but in practical systems, it will be replaced by some other pulses like root raised cosine filter, or it can be any realizable shape. And we will also assume gray coding for the mapping of bits to symbols throughout these series of lectures. And ES denotes the average symbol energy, which is given by this particular expression, which is 1 over m summation of EI, where EI is the energy of the ith symbol. So we will compute the average energy by adding all the energies of the symbols divided by the total number of symbols. So this is the concept of bandpass modulation. So instead of transmitting the baseband data, we will be transmitting this cosine with changing amplitude, changing frequency, or changing phase, or the combination of these characteristics. On the receiver side, it will be performing demodulation and detection. Demodulation is the process of conversion of the received data to the baseband data. It can be achieved either through match filter or through correlators. And the main idea is to perform correlation or match filtering through the use of basis functions. And basis functions, we have already discussed in the previous lectures that these basis functions are completely orthogonal of each other. And to transmit one out of capital M waveforms, we need to have at least capital N number of basis functions, where n will always be less than or equal to capital M. So this particular diagram is showing you the process of demodulation through the use of correlation. So the received data R of t will be multiplied with all of the basis functions psi1, psi2 up to psi n, and all these correlations will be performed to generate the sampled output z1 up to zn. And the receiver will be performing the detection block will be performing simply the thresholding to detect one of the transmitted bits denoted by m hat. This particular rule is called maximum likelihood detection rule. This particular architecture of the receiver has already been discussed in the previous lectures. Today we will be focusing on coherent detection. There are actually two types of receivers in communication systems. Number one is coherent and number two is non-coherent. So what is coherent detection? Coherent detection is a type of detection which requires carrier phase information for performing demodulation or detection on the receiver side. While non-coherent detection is the process which does not require the information of carrier phase to perform demodulation and detection. So there are some modulation schemes that need to perform always coherent detection, but there are some other schemes which may perform coherent detection or they may perform non-coherent detection. But in today's lecture is focused towards coherent detection, and there are some sources of carrier phase mismatch on the receiver side, due to which it becomes more challenging to use coherent detection. But definitely the performance of coherent detection will be superior as compared to non-coherent detection at the cost of increased complexity. And that complexity comes from the fact that the receiver needs to track the phase of the incoming carrier. And why this mismatch is created? It may be due to propagation delay that causes carrier phase offset in the received signal, or it may be due to the locally generated frequency from the local crystal oscillators. So due to the mismatch between the transmit and receive crystal oscillators, there may be a phase mismatch that can cause problems on the receiver side. And to remove this mismatch and improve the quality of the receiver, we use circuits such as phase lock loop. So this PLL. This PLL is one of the famous techniques to estimate the carrier phase and compensate it. So let's suppose to have a general architecture of this phase lock loop and the working of this phase lock loop. We say that if the received signal is given by this particular expression, which is the same as we have already discussed, cos of omega it plus phi I of t plus alpha. This alpha is the mismatch phase which is being created through the channel or through the crystal oscillators. So the purpose of PLL is to generate and estimate alpha hat. The purpose of the PLL is to generate and estimate alpha hat, so that PLL generates two carriers. The first one is cos and the second one is sine. So the cos is responsible for the input to the I branch of the correlator, and the second one, which is sine, is responsible for to be fed into the Q branch of the correlator. So when we use PLL on the receiver side, each branch will be converted into two branches, I branch and Q branch. In a typical correlator, there is only one branch for each basis function, but while using PLL, which is a mandatory part of each receiver almost in digital communication system, so each branch containing the basis function will be split into two branches. One is I branch and the second one is Q branch. I branch contains the carrier which is cosine, and the Q branch contains the same frequency carrier, but it is 90-degree offset, so that will be in the form of sine, and these two branches will be used by the correlators to perform further detection process. So having discussed the fundamentals of bandpass modulation and coherent detection, now we move towards the famous bandpass modulation schemes. So there are many ways to categorize bandpass modulation schemes, but the criteria that we will be discussing in these series of lectures is with respect to the dimensions of the modulation schemes. So we can categorize all the bandpass modulation schemes into three types. Either they can be one-dimensional, or they can be two-dimensional, or they can be multi-dimensional. So what is meant by these dimensions? They have a direct relationship with the number of basis functions that are mandatory to be used for the generation of transmit pulses. So one-dimensional waveform means those modulation schemes which require only one basis function for the generation of transmit pulses. And under this category, we have got amplitude shift keying, which is ASK, and M-Array pulse amplitude modulation, which is M-PAM, pulse amplitude modulation. So we will see shortly that how these modulation schemes are categorized into one-dimensional waveforms through the use of a single basis function. Similarly, two-dimensional waveforms are those, or two-dimensional modulation schemes are those which require at least two, at most, not at least, at most two basis functions for the generation of their transmit pulses S1 to Sm. So under this category, we have got M-Array phase shift keying, MPSK, and M-Array quadrature amplitude modulation, MQAM. So that QAM is basically a joint venture of amplitude shift keying and phase shift keying. And the third category is multidimensional waveforms. Multidimensional waveforms is the category which needs to have more than two basis functions, more than two orthogonal basis functions for the generation of the transmit pulses. And under this category, we have got only one scheme, which is M-Array frequency shift keying. So this is the broad categorization or classification of all the bandpass modulation schemes. In this particular lecture, we will be first focusing on the amplitude shift keying and M-Array PAM, or pulse amplitude modulation. So to start with, first of all, we see what is the basic model of amplitude shift keying modulation. And the first point regarding this is the generalized framework or generalized mathematical model of the transmit pulse. So the first equation here, which is Si of t, it is the ith transmitted pulse. It is given by 2ei over capital T square root cos of omega ct plus phi. So this is the general description of the transmit pulse which will be used throughout the discussion of bandpass modulation. Cos omega ct, this omega c is the carrier frequency, phi is any arbitrary phase. It is not containing the information. It is any arbitrary phase that can be generated through local oscillators randomly. And usually this phi is modeled as uniform random variable between 0 to 2 pi. Why we have used this 2ei over capital T square root as the amplitude? This specific notation has a particular reasoning, and let me show you first of all why we have taken this particular formation. So let's say instead of this thing, let me write it simply, for example, S of t in the form of a sine wave. I can write it as A cos omega ct. I am just ignoring the arbitrary phase to make things simple. So this A is the peak amplitude here. A is peak amplitude, as you should know that this peak amplitude is related with the RMS amplitude as under root 2 times the RMS value. Or I can also write it as under root 2 ARMS square whole square root. Now, assuming the standard 50 ohm model, this particular ARMS square, that can be replaced by the power of the sine wave. So in that particular fashion, I will write S of t as 2 times P square root cos of omega c t. Now, as power is defined as energy per unit time, so if I replace power with energy, that can be written as 2e over capital T square root cos omega c t. So that was the mathematical equation that I have shown in the slide. So this is the generalized description of any transmit pulse, and the same formation will be used throughout the discussion of bandpass modulation. Now, having gained the concept of this SI of t formation, now we discuss what is amplitude shift keying. So technically, amplitude shift keying is completely analogous to its counterpart amplitude modulation, which is used in analog communication system. And the basic concept of amplitude shift keying is the same as that of amplitude modulation, and that concept is that we are going to change or vary the amplitude of the carrier in accordance with the amplitude of the message signal, right? So as discussed earlier, that we are going to change one or more characteristics of the carrier in accordance with the amplitude of the message signal. So message signal or the waveform, transmit waveform. So here, because it is amplitude shift keying, so we are going to change the amplitude of the carrier. So now this was the basic concept of amplitude shift keying, and this concept can also be verified from the formation of this SI of t. You see, there is no parameter which is depending on the index I inside the argument of cos. It means frequency and phase are not changing with respect to the index I. There is only one thing which is changing with respect to the amplitude I, and it is EI, right? So it is also confirming the fact that this particular amplitude is only changing with respect to the amplitude of the transmitted bits, right? So now the next point is why it is one-dimensional pulse modulation scheme. And the reason I have already told you that it is only using one basis function for the formation of its transmit pulse or the carrier. So here, if we denote that single basis function as psi1 of t and write it as this one, 2 over capital T square root into cos omega ct plus phi. So if this is the basis function, this is the only basis function. So by using this basis function, we have already discussed in the previous lecture that each pulse can be represented by the linear combination of the basis functions. Since in this particular case we have got only one basis function, due to this reason it is simply a scaling of that particular basis function. So if the basis function is psi1 of t, we will only scale it with ai, and if you compare this particular equation with this particular basis function, there is only one difference of ei square root, right? So if I make ai equal to ei square root and combine these two equations, I will be getting this particular thing. So irrespective of the value of m array, the same equation will be used for the generation of transmit pulses, and ai will be equal to ei square root, and where ei is the energy of the ith symbol, right? So now if you take it as an example of drawing the amplitude shift keying signal, so let me write it again here, that Si of t was equal to ai into psi1 of t, where I is from 1 to capital M. So if we set M is equal to 2, this becomes binary ASK. Binary ASK, let me write it in capital, binary ASK, which means that either we will have S1 of t, which will be equal to A1 into psi 1 of t, or we will have the second pulse, which is S2 of t, which is equal to A2 into psi 1 of t. Now the value of AI will be equal to EI square root. So for binary ASK, we set AI A1 equal to 0 and A2 equal to some non-zero value of the energy E2. Let's call it E2, right? So in this particular way, if I draw the transmit pulse, so let's say the carrier cos omega ct is shown by this particular sine wave having constant amplitude, and if the transmitted symbols, because it is binary, so bits and symbols are the same. So let's say this is the symbol duration capital T containing 2 cycles like this. Let me make a change here because 2 cycles are completed here.